Thank you for introducing our presentation. My name is Jung from Korea University in South Korea. Let's start our presentation. Tropical cyclone projections are summarized in IPCC SROCC as follows. The starting point of our research is based on this item. The storm surge is an abnormal sea level rise due to low pressure and strong winds in tropical or extratropical cyclones. For grounded policy-making of coastal zone protection against storm surge in the future climate condition, it is necessary to identify future storm surge-prone areas on national or regional scales. When projecting future changes of tropical cyclone, by using general circulation model, there are uncertainties due to several factors. The range of uncertainties for each source can be accordingly different and needed to clarify. Regarding uncertainty caused by model resolution and physical parameterization, some recommendations have been proposed through the analysis on the model accuracy in global and ocean basin scales. On the other hand, few studies have assessed the uncertainties resulting from future sea surface temperature conditions and global warming scenarios. Moreover, the uncertainty in projecting future tropical cyclone properties varies according to scale and location of the region of interest. In order to evaluate the future storm surge risk at the national scale, it is necessary to evaluate typhoon characteristics for country-specific in prior to conducting storm surge simulation using them. So, the present study estimates the uncertainties in projecting a future storm surge height around the Korean Peninsula, which is located in Northwest Pacific using the Typhoon Data, which is extracted from ensemble experiment results of MRI AGCM 3.2H with different global warming scenarios and future sea surface temperature conditions. This is the research flow to achieve our research goal. We used the output of 7 ensemble experiments to evaluate the effects of the global warming scenario, which is represented by LCP scenarios and future sea surface temperature change patterns on the projection of future storm surge heights. Each ensemble experiment was abbreviated for convenience. The sequence of letters in the abbreviations following AGCM indicate the conditions of global warming scenario and the spatial pattern of sea surface temperature. The typhoon data was extracted from the results of its ensemble experiments by applying the TC detection technique by Murakami et al. was employed to project the future storm surge height around the Korean Peninsula. Here we focus on typhoons affecting the Korean Peninsula, which pass through this pink region. Reproducibility of typhoon characteristics like the number, track, and minimum central pressure was estimated by comparing with observed typhoon data (IB tracks). And future change of typhoon properties and its uncertainty was assessed by comparing HPA and HFA ensemble experiment results. The typhoon data from ensemble experiments were employed as external forcing for storm surge simulation around the Korean Peninsula. A series of storm surge projections corresponding to each typhoon event was conducted using storm surge model SWOT. The calculation domains were downscaled in 3 steps as shown in this figure. The results I'm going to introduce today are from domain 2 area. This is our result. First, reproducibility of the typhoon data in the past climate and its future change were evaluated. This figure and table show probability of the total numbers of the typhoons and the past and future climate conditions. The HPA and the estimate the number of typhoons affecting the Korean Peninsula. The typhoon occurrence frequency bias should be considered significant for projecting the typhoon frequency under the future climate condition. The future change in the typhoon frequency for each ensemble experiment is estimated by subtracting the typhoon frequency under the past climate condition from that under the future climate condition. So it was assumed that the frequency bias would be offset in calculating future changes of the typhoon frequency. The total typhoon occurrence frequency under the future climate conditions tends to decrease as greenhouse gas concentrations increase. While there was no big difference according to the sea surface temperature pattern, but only the HFA RCP85C1 showed a noticeable lower occurrence frequency. Next, the characteristic of Typhoon Tracks was assessed. Typhoon Tracks based on HPA was qualitatively in good agreement with observations. In all experiments under the future climate condition, it is anticipated that the typhoon routes will not change significantly depending on the future climate conditions, while genesis and lysis locations of the typhoons will move to the northwest and the northeast respectively. Finally, features of the typhoon intensity, which was expressed as a minimum center pressure of typhoons, were estimated. This study generated a wind field for such simulation using gradient wind field model with its typhoon events. So, characteristic of wind velocity of the typhoons are not considered here. Mean value of the probability density of minimum central pressure for HPA was smaller than IB-Tracks 1 by 8.8 hectopascal. However, this difference of the mean values of minimum central pressure between HPA and IB-Tracks cannot be ignored in storm surge simulations. No picture is presented here, as the points in the QQ plot of the mean value of minimum central pressure of HPA and IB-Tracks approximately lie on a line, so minimum central pressure for all ensemble experiments was linearly calibrated. The change rate for mean value of minimum central pressure in the future climate declined and is greatly affected by global warming condition than sea surface temperature condition. This figure shows spatial distributions of the future change of maximum storm surge height in the simulation period. Because it is hard to evaluate an extreme storm surge height with a specific return period such as 50 year or 100 year using time-slice climate experiments due to the lack of typhoon events. So this study focused on maximum storm surge height for the uncertainty assessment. The future changes of maximum storm surge height for ensemble experiments using different sea-surface temperature patterns present that those changes are strongly influenced by some specific high-intensity typhoon. Thus, applying different RCP scenarios shows similar patterns, but the range of the variation is different. These results indicate the sea surface temperature patterns and global warming scenarios would affect the typhoon characteristic in the future climate conditions, which could accordingly change future maximum storm surge height and vulnerable area to storm surge. Here, we analyze the contribution of the external meteorological force components of sea level pressure and wind formed by the typhoon to maximum storm surge height. Here, for experiments using multiple sea surface temperature conditions, the upper figure shows the maximum storm surge height induced by sea level pressure, and the lower one presents the ratio of the maximum storm surge height induced by winds to total maximum storm surge height. For each experimental condition, sea level pressure contributed about 0.2 meter to the maximum storm surge height, and no regional dependence was shown. By contrast, the maximum storm surge height induced by wind had a large regional dependence for each ensemble condition, and the spatial distributions of the total maximum storm surge height are similar to that of the maximum storm surge height induced by wind. For coastal areas in Korean Peninsula, the ratio of maximum storm surge height induced by wind to total maximum storm surge height was significantly higher than that by sea level pressure. This is our summary. For your information, today's presentation was published in Climatic Change in July of this year. The contents that were not fully introduced today are detailed in this paper. So thank you for your attention.